Okay, this is number 16.5, number 5, and it's the second question we're going to be asked to use divergence and curl to simplify a line integral, or at least express it as an integral of area instead of a closed loop integral. So for the first integral, where we're going to evaluate f dot dr, because this closed loop is pretty easy to work with, that's what we're going to do for the first one. We're not actually going to utilize the curl here. So let's go ahead and build the r function. So r of t is going to be equal to a circle of radius 1 to draw its boundary is going to be cosine t sine t between 0 and 2 pi. So that's our boundary function, and then of course I need dr so I can do the dot product. So dr is going to be negative sine t cosine t dr, or dt. So there we go, that's for our dot product, and then the function for our dot product is going to be y negative x. So y is sine t, so f, its x component is actually its y component, sine t, and its y component is negative x, so that's negative cosine t. And there it is, our dot product is just the product straight down. So if I want to evaluate the left side of this theorem, it's going to be the closed loop integral, and it'll be from 0 to 2 pi in t, and then it's going to be negative sine squared minus cosine squared, or negative 1 dt, and of course that produces negative 2 pi. And so that's the answer. So while forming the functions wasn't trivial, it formed an integral that was really, really easy. So 2 pi is the answer. Let's do the second one now. Now for the second one, I don't really want to compute that. It's the same RT because it's the same path. But again, this is, I don't want to go through the work to find the normal. So let's go ahead and compute the dot product, dA, and we'll do this one as an area vector. We'll probably be able to do it in polar coordinates. So I draw a line, and this is the second one that we're evaluating. So let's evaluate del dot f. So del dotted with f is going to be, again, the partial with respect to x, partial with respect to y, dotted with y and negative x. And I think you're going to see what happens here. The partial with respect to x of y is 0, and the partial of y with respect to negative x is also 0. So this dot product is equal to 0, and of course that's the argument here. So we're going to get the double integral. It doesn't even really matter what units I put it in, of 0 dA, and that's going to be 0. So it turns out I don't need to evaluate the second one, and had I gone through all the work of dotting the original f with its normal vector over this path, I would have found the same answer as 0. So this was beneficial in that it showed me that the argument for the integral is going to be 0. So there it is. For number 5, the answer to integral over the path of f dot dr was equal to negative 2 pi, and the integral over the path of f dotted with the normal vector ds was equal to 0.